Swayam Prabha. Digital India. Educated India.
To understand Miller-Prabha indices for directions, we will take up this example. As before, as in the case of planes, we will have 4 indices, the third index being the redundant index in the plane. So, let me show a projection of the basal plane and consider 3 basis vectors A1, A2 and A3, and let us try to derive the indices for this green vector in this Miller-Prabha system. You can see that this green vector is in the opposite direction of the A3 vector. Okay. The way I go about determining the Miller indices for the direction would be, I would take the projections along the A1 direction, the A2 direction, and so the projection along the A1 direction would be A by 2, along the A2 direction would be A by 2, along the A3 direction it intercepts at minus A, it's in the opposite direction, and as before I would factor out all the factors with respect to the lattice parameters. In this case, the lattice parameter along the 3 directions on the plane are equal, which is equal to A, and this is one of the important things we have already noted about Miller indices, that we never leave the lattice parameter. That means we never get irrational numbers with respect to indices, because a single lattice parameter A, for instance, could be 1.7 angstroms or one of those numbers, but I do not include those kind of units here, and therefore I normalize with respect to the lattice parameter. I get the values half, half, minus 1. Then I factorize this factor half out like we did for the planes. So I would get 1, 1, minus 2, and as before I would enclose them in the square brackets to indicate that it is a direction. So the Miller indices for this direction would be 1, 1, 2 bar, and the C direction it is 0, because we did not traverse along the C direction. So let me go through the procedure again for this green vector. I draw the green vector and use my 3 basis vectors on the basal plane. I take my projections along the 2 A1 and A2 vectors and also the A3 vector, but as you can see that I do not actually have to take the projection along the A3 vector, because I can derive them from the first 2 indices. Like here, the HKI, I is minus H plus K, so it is minus 1 plus 1, which is minus 2. So I do not have to actually determine this index, which is a redundant index. So I find the projections are along these 2 directions, A by 2 and minus A. I normalize with respect to the lattice parameters, take out the common factors, and finally write down the indices without any commas and putting the negatives as bars. So this is how I determine the Miller-Prabha indices for directions. Now we had briefly mentioned, and there was a question also regarding this, that what directions are perpendicular to what planes. And in the simplest case, which is the cubic case, we found that any HKL plane is perpendicular to a HKL direction. Suppose I take a 1, 2, 3 plane, then the 1, 2, 3 direction would be perpendicular to the 1, 2, 3 plane. So let me write this down. So correspondingly, any other kind of direction, for instance, suppose I can even choose a, for instance, 1, 2, 3 bar direction, this will be perpendicular to the 1, 2, 3 bar plane. But when we go to lower symmetry systems, we have to be little careful about what planes are parallel to or perpendicular to what directions, and in the tetragonal system there are only special planes which are perpendicular to some special directions. So for instance, the 1, 0, 0 planes are perpendicular to the 1, 0, 0 direction, the 0, 1, 0 is perpendicular to the 0, 1, 0, the 0, 0, 1 is perpendicular to the 0, 0, 1 direction. Then there are of course special planes like 1, 1, 0 is perpendicular to the 1, 1, 0 plane. But for instance, I cannot generalize this. The 101 direction is not perpendicular to the 101 plane. And so this is obvious, because suppose I am taking the projection. So this is my fourfold direction of the tetragonal system, and now my, for instance, this is my 110 plane. So this being my x-axis, A direction, this is my B direction, and I am taking a projection along the C direction. So this is my 110 plane. My 110 vector direction would be this, and you can clearly see that 110 direction is perpendicular to the 110 plane. But this is not true for all the other kind of planes, including 101 direction is not perpendicular to the 101 plane, okay, because there is a C elongation or a C contraction in the tetragonal system. In the orthorhombic system, we find that even lesser number of planes are perpendicular to even lesser. So only the 3 orthogonal basis vectors and their corresponding planes are perpendicular to each other. So the 100 direction is perpendicular to the 100 plane, the 010 direction is perpendicular to the 010 plane, and the 001 direction is perpendicular to the 001 plane. And if I have a general HKL plane, it will not be perpendicular to the HKL direction. So this has to be absolutely clear. In the hexagonal system, one obvious choice where the direction is perpendicular to the plane is the basal plane, the 0001 plane, which is perpendicular to the 001 direction. So since I have a model of the hexagonal system, I can show you that which direction is perpendicular to what. For instance, this is one special crystal made out of the hexagonal system, but nevertheless this would serve the example. So I have this basal plane, which is a 0001 plane, and my 0001 direction would be the direction which is perpendicular to this plane. So this is, however, an interesting note would be, this is, of course, this rule is the only plane being perpendicular direction is for the general C by ratio. That means I choose an arbitrary hexagonal crystal which has any given arbitrary C by ratio, then this is true that I have only one plane which is perpendicular to one direction. But there are special hexagonal crystals with special C by ratios, and this is, for instance, if you choose hexagonal crystal or hexagonal lattice with √3/2 as the C by ratio, then you have the cubic rule which is followed. So these kind of special kind of crystals are called pseudo cubic crystals because they have the cubic rule being followed, and the special ratio is often referred to as the Franck's ratio, wherein √3 of course being the length of the body diagonal of the cube and √2 being the length of the face diagonal. So it's √3/2, and if my hexagonal lattice has this crystal has this C by ratio, then I have the cubic rule being followed. In the monoclinic system, the 010 is perpendicular to the 010 plane, and as you go down to even lower symmetry ones, you note that in general you cannot assume that a HKL plane will be perpendicular to the HKL direction. So this is in general true, and except there are such exceptions, for instance the cubic, tetragonal, orthorhombic and hexagonal systems, wherein we identify certain planes which are perpendicular to certain directions. So therefore we have to be absolutely clear, and we have to play a lot of caution in understanding that what kind of a crystal system or what kind of a lattice we are dealing with, and then make our conclusion regarding perpendicularity of directions and planes. Next we come to an important law, which is, at least the way it is called the Weiss zone law. So the Weiss zone law states, if a Miller plane HKL contains the direction UVW, then HU plus KV plus LW is equal to 0. So I am talking about a general Miller plane HKL, and I am talking about a general plane UVW. Then if this direction lies in this plane, then HU plus KV plus LW is equal to 0. And of course when I say lies, it can, of course, you know that a Miller indices, the plane can, or the direction can always be translated parallel to itself, and therefore the condition would still hold good. And the important thing is that this relation is valid for all crystal systems. Now to understand this relation, let us take up a solved example which will also clarify some of the points about these planes and directions. And in this case I am talking about a cubic system in which I am trying to find the intersection of the 111 plane with the 111 bar plane. So I want to find the Miller indices of the direction which is the intersection of these two planes 1 1 1 and 1 1 1 bar. Now we have to remember that of course when I am talking about a 1 1 1 plane, I am talking about a set of planes, but still to make sure that I consider the appropriate plane, not a parallel translation, so that they exist in the unit cell which I am describing, so that I can keep my intersection in the first unit cell. So you can clearly see I have chosen one of the set of parallel planes so that my job in hand becomes simplified. So I will use one graphical method and two analytical methods to solve this problem of the intersection of the 1 1 1 plane in the cubic system with the 1 1 1 bar plane. Graphically, however, I of course draw the 1 1 1 plane, and then I could of course draw the 1 1 1 bar plane in the unit cell below this, or in the same unit cell, or the unit cell behind. For simplicity, I have drawn it in the unit cell right below it to make visualization simple. Of course, I could have also drawn it within the same unit cell. So you can see the 1 bar plane has intercepts as 1 along the x axis. So my origin is somewhere here, this is my origin here, and this is my x axis, this is my y axis, z axis. Therefore it has intercepts 1 along the x axis, 1 along the y axis, and minus 1 along the z axis. So graphically you can see that these two planes, the blue plane and the green plane, intersect along this line. So obviously as far as the Miller indices goes, there are two choices, either the direction this direction or its negative, and both are solutions to this problem of intersection of these two planes. So as for direction go, there are two directions. The line of intersection of course just will be one line, which is the red line. Now once I know the line, I can find its direction. Suppose I take this as the origin, I take this as the head of the direction, then I know the vertices of this is 1 0 and this will be 0 1. So I subtract 0 1 from 1 0, I get 1 1 bar 0, and therefore I enclose it in bracket. The opposite direction is best by taking negatives, so I will get 1 bar 1 0 as the opposite direction. So the line of intersection would be 1 1 0, 1 bar 1 0 or 1 1 bar 0. So this is a graphical simple method of finding out the intersection of the two planes. Now to illustrate the utility of the Weiss zone law and sometimes its simplicity, let me solve the same problem by using the Weiss zone law. And let me assume that if the direction is UVW and it is contained in the plane HKL, according to the law it is HQ plus KV plus LW. In this case I know both the HKL planes, what I do not know is the direction UVW, right. That means these are both these HKL planes have this direction in common, this UVW direction, but it is the direction which I am trying to determine from this Weiss zone law. So the UV direction, let UVW be the direction of intersection of 1 bar 1 bar 1 and the 1 bar 1 bar 1 bar plane. Of course I have just taken the negatives of these planes, which would of course not alter my arguments, just to enrich the kind of point which I am trying to make, that sometimes I would like to consider the opposite set of planes, and whenever I am talking about planes they are always a set of planes. So as far as the intersection with respect to the 1 bar 1 plane, it is minus u minus v plus w equal to 0. Intersection with respect to the 1 bar 1 bar plane will give you minus u minus v minus w equal to 0. Solving them simultaneously I will find out w equal to 0 and u equal to minus v. So the indices of the direction of the form u bar 0. Of course when I write Miller indices I always factor out the common factors, so I can write it as 1 1 bar 0, and as I see the negative of this direction also is a valid choice, so it will be 1 bar 1 0. So let me go through this analytical construct or the Weiss zone law method of solving once more, keeping in mind that often it is instructive to use the graphical method wherever possible in addition to any of the analytical solutions, because that gives you a better visualization of the problem. And also, for instance, when I draw this direction 1 1 bar 0, I can see what atoms are sitting on this direction, what is its importance in terms of, is it a close packed direction, is it not a close packed direction. All these questions can be answered when I use a graphical method. So always a multiple method of solution not only makes sure that you have solved the problem correctly, but also helps you in understanding the importance of these planes and these directions with respect to the crystal.
So every crystals have some planes and some directions, and in some planes and directions some are perpendicular to each other and some are not. But by this law we can find the number of planes which are perpendicular in any crystals or which are not.
Okay.
This law cannot state about.
Yeah, in cubic crystals this automatically leads to the fact that when I am talking about a UVW direction, I can find the angle between the two, and I will find that the HU plus KV plus LW is valid. It is valid for cubic crystals also, because now the HKL direction will be perpendicular to the HKL plane, and since this direction is now perpendicular to this direction, the HKL direction will be perpendicular to the UVW direction, which is on the plane. I can use a perpendicularity concept to arrive at a similar kind of equation. Now let me go through the Weiss zone law once more. If now my direction is UVW is a common direction between the two planes I am considering, and I, for instance, just for the sake, invert the direction of the, or invert the signs of these two planes. Instead of considering the 1 1 plane, I consider the 1 bar 1 bar 1 bar plane, and instead of the 1 1 0 plane, I consider the 1 bar 1 bar 1 plane, which is not going to alter the solution as I want to show you. And now I take into account that this direction is common to both these planes, and I apply first to the first plane and then to the second plane. I get two simultaneous equations, solve them, and I get, and since there are three unknown variables and there are two equations, I will not get a unique solution from this, but I come to know that W is 0 and U is equal to minus V, and therefore I can write the indices of the U bar 0. But since, if this is true, it is also true for 1 1 bar 0, which is what the least index I can choose for. Therefore I know my direction of intersection is 1 1 bar 0, or its opposite direction 1 bar 1 0. And an alternate method, analytical method, to solve the same problem would be to use our common understanding of coordinate geometry. So here I am going to use an equation of a plane. For instance, an equation of a plane with intercepts along the x, y, z direction is given by x by a plus y by b plus z by c equal to 1. This is an equation of a plane in the form in which a, b, c are its intercepts along the three coordinate axes. Now I know that I have two planes under consideration, and I need to find the common direction. So let me write down, substitute the two planes which I am the intercepts of the two planes, and my intercepts are, for instance, for this plane is 1 1 1 and this is 1 1 1 bar, and substitute them. So I get I putting the intercepts inside, I get two simultaneous equations. Okay. And now of course I have taken the negatives of those, and I can get a solution of the common equation, which is minus 2x minus 2y equal to 2, which, writing in a different form, it's x plus y equal to minus 1, and even further writing it in a different form, I will write it as y equal to minus x minus 1, which is in the typical form of y is equal to mx plus c, which means that my slope is minus 1 and my intercept is minus 1. So my slope is minus 1 and my intercept is minus 1 along the x direction. So this is my x direction, this is my y direction, slope, intercept is minus 1. So this is my, I have plotted the equation of my line y equal to minus x minus 1, and since I am talking about directions which are a parallel set, I could even translate this and put it here and determine the Miller indices, or determine here, it would not matter. So I could now write down the Miller indices of such a direction, either the positive or the negative, as 1 1 bar 0 or 1 bar 1 0. So I have more than one method at my disposal to determine the Miller indices of the intersection, but as you can see, each one of them is instructive in a certain way, and typically if I were to solve this problem, I would use either the graphical method and also the analytical method, but also you can use your familiar coordinate geometry, which is the equation of a plane in the intercept form, and then solving for the there are two planes, and then I find the common direction by solving simultaneously. That means that is that one line which is common to both the planes. So I solve for that and then write it in the y equal to mx plus c form, plot that equation, plot that line, and then find its Miller indices. So I could do that, and I find the same thing, the Miller indices 1 1 bar 0 or 1 bar 1 0. So with this we come to the end of a set of what you might say lectures on Miller indices, and as I said, it is Miller indices is merely a tool, and it is typically used to represent directions, planes, and we also seen what are the important planes and directions which we need to keep in mind when we are talking about the basic crystals, and we will connect with the importance of some of these when we actually talk about, we have already been doing some of these already with respect to crystals, but when we really talk about crystals, some of these planes and directions, the low index ones, are very important with respect to some of the properties, and therefore we need to keep Miller indices language in our mind when we are dealing with crystals. Next chapter we are dealing with the structure of solids. Here we will start with a broad overview and then go on to metallic solids before we take up ionic and covalent solids. We shall specially focus on some of the rules of formation of, especially like for instance ionic solids. We will worry about the kind of bonding in these kind of solids, and some of the concepts would just be a revision of something we have dealt with before. But special care should be taken when you in this chapter, because some of the concepts might look familiar, but we will be dealing with additional concepts and which will be interweaved with the previously existing concepts, and therefore we should not be less attentive because some concept seems familiar. So what is that we plan to learn in this chapter? We will try to understand how matter can be classified, and this will be a very broad overview, and often some of these concepts we will not deal with in this elementary course, but it is good for a student to know that there are these additional things, and some of us later on may want to worry about these. We would like to know how to classify crystals based on bonding. We already seen about bonding in materials, but this is especially a classification of crystals based on bonding, and some briefly we will consider how things may, for instance, amorphize or stay crystalline. We will then take up some important metallic structures, of course some of which we already considered, for instance the cubic close packed and the body centered cubic, etc. Then we will try to understand the structure of alloys, especially the concept of ordering and disordering in alloys, and later on we will talk about ionic solids and covalent solids. So when you are talking about classification of atomic state of matter, we can use either the band structure classification, wherein we know a material can be classified as a metal, a semi-metal, a semiconductor or an insulator. So this is purely from the band structure point of view, and in this course of course we do not go into details of this aspect, but we should note that suppose I am talking about the state or viscosity aspect of classification of atomic state of matter, then I have the familiar gas, solid, liquid picture. Further, what I am interested in this particular course is the structure of solids, and if you look at the structure of solids, on one hand we will see that there is this concept of crystals which we have been dealing with quite a bit so far. On the other extreme is the concept of amorphous materials, in other words which are totally disordered. Okay. There are other structures possible, like for instance things between liquids and crystals which can be called liquid crystals. We will again not deal in too much depth in this course about liquid crystals, but it is worthwhile to note there are states of matter which are between liquids and crystals, and often our language of crystallography, our understanding of atomic structure can be extended in various ways to incorporate these liquid crystals. In fact, but of course they also pose new challenges, and new kinds of defects can be found in these kind of liquid crystals. Often we are talking about classification not just based on symmetry, which is now wherein we are talking about crystals, but we are also taking into account the size, in which case often people talk about nanocrystals, wherein the grain size or one of the atomic entity size is very small. Now this course will not deal with depth with another form of matter known as quasi-crystals, but it is worthwhile to note there are states of matter which are quasi-crystals, which are distinct from crystals, and also which are distinct from amorphous states of matter. Now what characterizes these three important states of matter in the solid state? The atomic, based on atomic arrangement, we are talking about crystals which are ordered and periodic, and of course we have already given a very formal definition of a crystal based on the lattice plus motif, but we know they have the characteristic that they are ordered and periodic. Amorphous structures are neither ordered nor periodic, and of course we also saw examples wherein we could see that there was some positional order, but there was no orientational order, and put together the positional and orientational order, we call them amorphous structures. Quasi-crystals have a property that they are ordered, but they are not periodic, and often such a structure is sometimes called quasi-periodic structure, but this course will not take us into detail into the quasi-crystals, but it is important to note there are these kind of additional structures, and which are often associated with disallowed crystallographic symmetries. That means quasi-crystals can not only have allowed crystallographic symmetries, but can also have disallowed crystallographic symmetries, but all of them do not have any kind of periodicity. It is important to note that typically it is stated that a crystalline state, and now I am comparing my crystalline state with the amorphous state. Okay. So assuming that I am comparing my crystalline state with an amorphous state for say a material of a given composition, then it is stated that at least there is one crystal which has a lower free energy than the amorphous state. So therefore, if I have a amorphous material, and sometimes the term glass is also used, it will be noted that such a material would want to crystallize. So that is an important point to note. Certain aspects of crystals you already know, that they have a sharp melting point and they also have a higher density than an amorphous phase constructed of the same composition. In this chapter we will mainly deal with crystals, but in the passing we will also talk about conditions under which amorphous structures can form. We already noted that a crystal is characterized by both positional and orientational order of the motifs and of the which can be a physical property or a geometrical entity. Just perhaps we have not introduced so far is the range of the order. Often the order we are talking about could be the complete long range order, which means the entire material pervading across the entire material perhaps, or some smaller entity, but definitely much larger in length scale compared to the atomic entities we are talking about. But there could often be just short range order, and this is something important to note, and we will see that there could be materials which have long range order but no true short range order. There could be materials with short range order but no true long range order, and all these possibilities exist, and therefore we should be clear that what kind of an order we are talking about when we are dealing with the kind of crystal. To understand, for instance, give you a somewhat of a simplified example, it is often found very difficult or counterintuitive to understand that how can we have long range order but no short range order. It is easy to understand that we can have short range order but no long range order. So this is a simple concept to understand, but the reverse, that how can I have long range order but no short range order? It may come as a surprise that every single crystal we have in nature, that means any single crystal we have produced, actually has short range disorder and actually has only long range order. This is something which we note, but I will explain using a simple mathematical example. Suppose I have a sine wave which is my ordering function, just for the sake. So now this is my very well ordered function, it is a sine x, so I am plotting. So this is my sine theta, and let's say this is my theta or x. Now suppose on top of it, so just to make sure that I going to x to infinity, I will put it as x instead of theta. So now this is perfectly ordered function in the long range. Now suppose I overlay some kind of a noise on top of this function. So let me take a different color to illustrate that noise. Even though there is a lot of noise as far as each point is considered, you can see that the overall long range order is obvious to you, right? So this is an example wherein there is a lot of short range disorder. That means I am talking about length scale this small, I will not find any order, but on the long range I find order. In fact, in real crystals, at any finite temperature, you know, there is thermal vibration. That means atoms are vibrating around their atomic positions. Therefore, in the short range, if I freeze my time picture, then I will see that no atom is truly located at its lattice point. So there is short range disorder, but we know crystals still have the long range order. So since this was a point which seems counterintuitive at first sight, I wanted to explain this aspect, that you can actually have short range disorder and still have a long range order. Of course, you can even think of a situation wherein you have short range disorder and a long range quasi periodic order, but we will not deal with those kind of situations in this course. The aspect of orientational and positional order we have already talked about, but we will take up some more examples to see how we can understand these crystals. We will introduce one more concept, the concept of probabilistic order. So far we have talked about orientational order and positional order, but we will take up another kind of an order which is known as the probabilistic occupation. Now we will actually take up examples, and this particular concept of probabilistic occupation based order would be very useful in describing disordered alloys. Okay. And one more concept regarding when we are talking about order is that we could talking about temporal order or spatial order. So this is again something which we have to keep in mind. Typically so far we have been talking about spatial order, but we have seen, suppose I am talking about a liquid, the spatial order keeps on varying. We will see that, for instance, liquids typically have a short range order, but this short range order is not fixed in time. So there is a region wherein I could find, for instance, an atom with some kind of an coordination shell which is ordered, for instance an icosahedral coordination shell. Then at a different point of time these atoms would break apart and go and make a different kind of a short range order region. That means the temporal picture is varying, but the same short range order could be found in one region initially, then a different region later on. So the time picture is varying, but if I take a single time picture, sort of a snapshot, then I would see that I can have the short range spatial order in liquids. So I would again have to so though some of these concepts may not be immediately relevant, but it is, as I said, we are starting with a broad overview of all the concepts, then we will use all the concepts which are relevant for studying our immediate crystal set or the simple ones we are going to deal with. So when you are talking about true order versus probabilistic order, this is perhaps a illustrative slide which will put in perspective what I mean by orientational order, positional order, orientational order in the true sense, orientational order in the average sense, positional order in the true sense, positional order in the average sense, and finally probabilistic occupation order in the true sense, or how do I define my probabilistic occupation order. So this example of a crystal we have seen before, wherein you have set of arrows which are at lattice points all ordered perfectly. Now this kind of a thing is, obviously you can see it is positionally and orientationally ordered crystal, the one on the top. Now this could be, for instance, a picture of all the magnetic spins aligned in a ferromagnet within a domain. So I could get a picture like that, but then suppose you would see that suppose I heat such a material, then you could see that slowly some of the spins may get disordered. Nevertheless, you would see that there is a net magnetization in the material, and therefore I do not want to throw away my concept of a crystal. Suppose I stick to my strict definition of orientational order and strict definition of positional order. Such a material below would not be classified as a crystal, because now it does not have orientational order, it has just mere positional order. But still, as you can see, most of the arrows are pointing upward. So in the average sense, it is still orientationally ordered, though not as perfectly as the crystal at the top, but it is still ordered to a large extent. And I do not want to throw away all my knowledge of crystallography or all the description of this crystal using crystallography, so I will deal with this as an average crystal, or a crystal with average orientational order. The positional order similarly can be perfect, as you can see here, since these are spherical entities, so I do not have to talk about, or circular entities, I do not have to talk about a orientational aspect to this kind of an crystal. Now in the average sense, you can see that some of these atoms or spheres or circles are not exactly sitting at the lattice point, they are somewhere around the lattice point. But you can see they are within certain region of strike around the lattice point, so they are still ordered in the average sense. So this is the picture I was giving for instance thermal vibration. So at any instant of time, for instance, atoms may not be sitting at the lattice point, they may be away from the lattice point, but still in the average sense they are around a lattice point. So even in these cases I can consider this as an average positionally ordered crystal. So I can have true orientational order or an average orientational order, true positional order or an average positional order when I am describing crystals. The third description, the probabilistic occupation description, is perhaps very intriguing and very useful when you are describing disordered alloys. So I can have a truly ordered system, wherein, as you have seen, this would be a lattice point, it is a one-dimensional crystal, for instance, with a two-dimensional motif. Now my lattice points would be the centers of this red circles, and my motif would be one red circle and one green circle. Okay. Now this system could get disordered. So let me draw one possible disorder of this kind of a system on the board, so that we understand that what is that we are describing here. So as you can see, in the ordered system we had half the number of green circles and half the number of red circles. Now so let me So, I have randomly put some 4 red circles and 4 green circles, and you can clearly see here that if I were to treat this perfectly in terms of my language of crystallography, this is an amorphous structure because there is no unit cell. And if I go little farther here, for instance, there are 2 greens here separated by 1 red, later on and here there are 3 reds separated by 2 greens. There could be another red or a green here, there could any one, but I am overall putting 50% of my spheres as red and 50% as green. So, let me shade them for better visibility. So, I have an array of points. For instance, just I could have an array of points which are spaced A, and randomly I put 50% red and 50% green circles on those points. Truly speaking, in the true language, I have a disordered structure which I would call amorphous. That means it is not a crystal. But I will introduce this concept called, I am talking about a probabilistic order. That means I know, because I have a composition which is 50% A, say for instance 50% red and 50% green. So, my composition is so it's here the composition 50% red and 50% say R and 50% green. So, I can make, I know if I take any random point, there is a 50% chance of finding A or a 50% chance of finding B. Therefore, I can describe my structure here saying that at each lattice point or each point, now I have a probabilistic occupation by 50% green. So, this is green and this is 50% red. So, each point there is a probabilistic chance that I find A or B 50%. So, this kind of a probabilistic picture is what I am introducing, and when I draw a probabilistic picture, I get the picture as shown at the bottom of this figure, wherein I draw each point occupied by 50% A or 50% B. Now, what is the structure on the top? This is a crystal, a perfect crystal, which is positionally of course ordered, which has a lattice parameter. For instance, the red to red distance is A, for instance, or if I take this picture, it will be 2A. I am taking A as the length from here to here, then it will be 2A. Now, the lattice parameter of the probabilistically ordered crystal, in other words, the bottom crystal is only a crystal only in the probabilistic sense. In the true sense, it is amorphous. What is the lattice parameter of this? It is A, it is not 2A, right? And each site is now occupied by a motif which is forming this crystal, which is now not half a red plus half a green. That is not the right description of this motif, because you cannot, suppose these were real atoms, then I cannot cut half a green atom and stick it to another half red atom and put it to each lattice point. That is not the picture I am showing here. There is a 50% probability of finding the, for instance, the red atom and 50% probability of finding the green atom. Of course, you could have an entity when there are 3 atoms, there could be 4 different entities you could be dealing with. So, when you have instead of 2 entities, for instance, you could have many entities, and they could all form a disordered crystal, and you would then still use a language of crystallography, noting that now I am defining the crystal based on probabilistic occupation. Soumya had a question.
So, here in probabilistic occupation, is it required that the composition is already 50% or it can be for any composition in general?
Okay. The question Soumya has got is that, do I need to have 50% composition, or it can be any composition, or, and let me add some more to it, the question, can there be more elements than what I am describing here, which is what I was mentioning. So, obviously the composition can be anything. So, instead of having, suppose in this same example, suppose I had, instead of putting, let me make one more of red, and assuming that this is my composition I am going to maintain. So, for every 3 plus 2, 5 red, I have 3 green. So, my composition would be red 5, green 3, right. So, my sphere, the probabilistic sphere now would be, or the probability circle now would be not be equally divided. So, I will have to divide it in 5 plus 3, 8 parts, okay, which I am perhaps can do it, right. So, I got 8 parts to my circle, and my chance of finding green is 3, 1, 2, 3. So, I will mark 3 of these in green, and the remaining, which is 1, 2, 3, 4, 5 is my red. So, this is my probabilistic occupation of a single lattice point. Of course, instead of having, I could add one more entity like a blue entity, for instance, to this whole picture. So, now my crystal consists of green, red and blue, and they could be completely disordered, for instance. So, I need to add some probability for the red presence of blue also, which would be some part of the circle, probabilistic occupation. A further interesting possibility exists is that suppose I have 3 elements, okay, as before, like in the case of the blue and green. So, this is a kind of picture wherein I have stoichiometry, it is 50% green, 25% red, 25% blue, right. So, I have, let me write that down here, 50% green, 25% red, 25% blue. One of these sublattices is completely ordered. This sublattice wherein the green is sitting is completely ordered. So, greens perfectly sit in lattice positions, but the second sublattice is now probabilistically ordered with respect to the reds and the blues. So, if I take one particular region of space wherein this crystal existed, I would see, for instance, this could be red, this could be blue, this could be blue, this could be red, but so that half of these positions are occupied by half red and half the other blue. So, now I have a description of a crystal with 2 sublattices. One sublattice is fully ordered with green, the other sublattice being ordered probabilistically with respect to the red and the blue. So, this is a possibility, and in fact, you often find crystals wherein one sublattice is completely ordered, the other sublattice is disordered with respect to 2 atomic species, which in general could turn out to be even 3 atomic species.
Sir, if we consider this probabilistic occupation description, then if we can consider any percentage, doesn't it mean that any amorphous material can be described as a crystal?
Very good question, very good question. Now, the question is that, let me rephrase Kavita's question. The question is that if any composition can be accommodated by a probabilistic picture into a crystalline framework, can't I consider every amorphous phase as crystalline? No. What is the starting point for all our crystalline picture? Complete positional, complete orientational order, right. In amorphous structures, there is no positional order, normal amorphous structures. We have been taking some very special cases wherein there is positional order, but one of the orders doesn't exist, and I call it amorphous in a very special sense. But for I take a general amorphous structure, for instance a window pane glass, then there is no positional order. Under no circumstances I can even associate an average position to any of these structures or an average probabilistic occupation. So, that is not possible for all structures. Under very special circumstances, and therefore, what I want to do, I do not want to call this an amorphous structure, but I still want to use my language of crystallography, which can be done. As you can see that there are these positions where atoms are located, and I often find it in A or B, and at the local most scale, suppose these were real atoms, then you would obviously notice that the local regions would be distorted. Suppose one of the spheres is big, one is small, then a region which has 2 big spheres would be spread apart compared to a region which is one small or two small spheres, right. But what I am doing, therefore when I am talking about probabilistic occupation, here I have taken equal size circles, which is not the case with real atomic materials. You will never have two different atoms of the same size. Therefore, there will be atomic distortions at the very local scale, but we average them also out, and we say that we talk about a long range region wherein I can describe it in terms of an average lattice parameter. So, this A also becomes an average lattice parameter. So, that thing has to be kept in mind. But these are very important questions which we should bear in mind when you are describing these kind of crystals.
Sir, I have one confusion. Suppose there is one polymer such PET by which we can form a bottle, and I have calculated I have got some 40% crystality in the PET material, but most of the persons called this is a amorphous material. So what will be the cut line of percentage of this crystal?
Okay, so here we are asking Mr. Patel as a more sophisticated kind of question, how do I go about describing percentage crystallinity, especially in more complicated systems like polymers. Now polymers themselves are long chain molecules, and typically they never become fully crystalline. So we have to often describe these kind of crystals in terms of percentage crystallinity. I think this is a much more advanced question at this stage. So maybe we will take it up at a later stage when we are actually in a position, perhaps when we have all the tools of crystallography and the tools of average ordering under our control. Okay. Again, let me give a broad overview of some of the states of matter which we have come across, various kind of crystals and amorphous things, and we will try to compare them in terms of the short range order and the long range order. So in this table, for instance, I have got crystals, quasi crystals, I have glasses, liquids, we even have a biological entity like a crystallized virus and gases, and we want to compare their short range order with and long range order. Some of the easiest one to do are the crystals there, and as I pointed out, when I am talking about order, now we are still in some sense in the perfect order of our mathematical sense. We are still not relaxed our order into the more some of the descriptions we have seen just now. We are still talking about some mathematical sense. So you can see the one extreme would be crystals and quasi crystals which are ordered in the short range and in the long range, and the other end would be gases which are neither ordered in the short range or in the long range. So gases are the other extreme, wherein of course we already know that they don't even have any kind of temporal order. The temporal order is always changing. A crystallized virus, for instance, and there are other examples in this class like colloidal crystals, artificially created macroscopic crystals, some of this, like, and they would come under this class like the crystallized virus. They are disordered in the short range. That means that within a virus entity there is no order, or no order in the real sense we are talking about here, but they could be ordered, and all these virus entities could be ordered into a long range crystal. These glasses and liquids, and when you are talking about liquids, we note that liquids have short range spatial order but no temporal order. So glasses, so I am talking about a snapshot picture of a liquid which can be compared in some sense to a glass, where you have the short range order but no long range order. So where therefore we can see that there are various kind of entities which are ordered in the short range or disordered in the short range, and the special class which we are dealing with in detail here are the class of crystals which are ordered and in the short range as well as the long range. So we should keep that when we are studying this, there are other kind of materials and other kind of possibilities, and often these are equally interesting possibilities. Though we are, as I pointed out, that we are dealing mostly with crystalline materials, and but still we would like to know under what circumstances would I form a crystal, and in other words, what are the opposite of those circumstances which will lead for the formation of the amorphous or the glassy state. So when primary bonds are one dimensional or two dimensional and secondary bonds aid in the formation of crystal, this kind of condition is preferred for the amorphous state. And if a crystal structure is very complex, and that means that precise ordering is very difficult, again you would tend to form an amorphous structure. These amorphous materials, as I sometimes told, are also called glasses, and the distinction often is made by the presence of a glass transition. And some materials, you would notice that there is actually a distinct glass transition which can be observed in a differential scanning calorimetry scan, or there could be materials wherein you wouldn't see this distinct glass transition, wherein crystallization takes place before the glass transition can take place. When the free energy difference between the crystal and the glass is small, then the tendency to crystallize would be small. There are kinetic factors which promote the formation of glasses. For instance, a fast cooling rate would be good for formation of glasses because you don't have enough time for the formation of crystal, wherein you require precise ordering. If you want to cool certain alloys to form glasses, which would be, say, for instance, metallic alloys, then you need to employ very high cooling rates like 10 power 6 Kelvin per second, which can be used by methods known as flat cooling, or by taking actually a fast rotating copper wheel and throwing a molten pool of metal on top of it, which is called melt spinning. But there are other materials like silicates which have a natural tendency to form glass very easily. That means you can take a silicate material, which is the common plate glass material, and cool it slowly, and still you would obtain a glassy substance. So, though far we have never dealt with how to form a glass or how to form a crystal, but then we have to keep in mind that even though a crystal, with respect to any amorphous phase, at least there is one crystal which has the global free energy which is lower than that of the amorphous phase, but reaching that global minima may not be easy. For instance, suppose I can leave my window pane glass for geological time scales at room temperature and still it may not crystallize. So, there are kinetic factors which come into play, and that will tell you that how easily can I form a crystal, how good will that crystal be in terms of its quality, in terms of its positional and orientational order, okay. And therefore, the crystal, those materials which have poor tendency to form crystals may not be fully crystallized, and in fact they may often turn out to be amorphous unless special care is taken to crystallize them. On the other hand, there could be materials which crystallize very easily. For instance, pure aluminum would crystallize very easily, and you want to obtain aluminum in pure form in amorphous state, then you need to employ very difficult techniques, and it is not easy to form amorphous aluminum. So, there are these both extremes, and therefore, I need to worry based on these kinetic factors is the quality of the crystal I have obtained. When you want to classify crystals, and this is one particular kind of classification which is often very instructive, is that we can classify crystals as molecular crystals and non-molecular crystals. Now, this classification becomes all the more important when you are talking about, say, certain properties like melting point and certain other properties like deformation, behavior, etc. Molecular crystals are typically made of molecules, and these molecules are formed by typically primary bonds which are covalent bonds. These molecules then go on to make a crystal using bonds which are much weaker, like the van der Waals bond or some other weak interaction, and therefore the bonding which is responsible for the formation of the crystal itself is actually a very weak bond. And there could, of course, this automatically implies that typically molecular crystals have a low melting point and they are easy to deform, and they typically turn out to be very soft, because the bond which is responsible for the formation of the crystal, which is opposed to the bond which is formation for the molecule, and now the molecule itself is the atomic entity which can perform the role of a motif in formation of the crystal, that itself cannot be broken down, but the weak forces which are forming the crystal, that can be broken down very easily, and therefore such materials have very distinct characteristics, the molecular crystals, compared to non-molecular crystals. If you look at the bonding of non-molecular crystals, they could be predominantly covalent, they could be ionic or metallic, and we have to remember that typically there are, of course, examples wherein the bonding is almost truly metallic, but in general real crystals could have bonding characteristic which lies somewhere in the phase triangle of metallic, ionic, covalent. In other words, what I am saying is that these three bonding characteristics, covalent, ionic, metallic, represent extreme forms, and actual bonding in crystals could have a mixed character, and we will take up some examples of this later on in the chapter. Another point to be noted is that though we are dealing with classifying crystals and we are using the word metallic in this context, for instance, we could have, for instance, metallic crystals and also liquids which are metallic. We know that mercury at room temperature is a liquid, but it is metallic. And so, to emphasize once again, we could have, for instance, ionic liquids, we could have metallic liquids, and therefore, we should not confuse these terms as restricted only to crystals. So, here we are talking about crystals in molecular and non-molecular forms, and there could be non-molecular crystals which have, for instance, ionic bonding or metallic bonding. But we could also have liquids which have metallic character, and additionally we could have amorphous materials which also have metallic character. For instance, there is a composition here containing zirconium, titanium, copper, nickel, beryllium, and this composition can be easily formed into a metallic glass which is known as a bulk metallic glass. In other words, I could attain macroscopic sizes of this metallic glass by slow cooling. So, some of these compositions, for instance, you can cool at the rate of 1 Kelvin per second or slightly more, even 10-20 Kelvin per second, and obtain a glass. That means that suppose I take a composition like this, melt it and pour it into a copper mold, I can get, for instance, a glassy material. Of course, I will not make the copper mold too thick, I would like to make it somewhat thin so that the walls nearby can extract my heat, but still these materials can easily glassified or made into a bulk amorphous alloy. So, I have to remember that crystals can be molecular or non-molecular. Molecular crystals have primary bonds which form the molecule typically as covalent, but the interatomic forces or intermolecular forces which lead to the formation of the crystal are van der Waals type or other weak kind of interactions. Non-molecular crystals could have covalent, ionic or metallic bonding characteristics, and typical crystals could also have a mixed characteristic between metallic, ionic and covalent. And important thing to remember is that we could have liquids and amorphous materials also which have certain bonding characteristics which look in terminology similar to the non-molecular crystals. So, we should not confuse for instance a metallic crystal with a metallic liquid or a metallic amorphous alloy. The metallic bond is very different from the ionic and covalent bonds. So, therefore, I would like to, when I am looking at the sub picture, and we will, as I said, in this whole picture typically we will be dealing mostly with non-molecular crystals. We will not deal with many examples of molecular crystals, though we will take up 1 or 2 examples to illustrate what are molecular crystals, but typical examples would be for non-molecular crystals. So, from the bonding picture I would like to classify the whole the picture as metallic and non-metallic crystals. Now, this picture is important to note because in metallic crystals, for instance, each element, for instance copper, going on to form the metallic crystal would donate electrons, and this electron would form a sea of, and therefore each electron now belongs to the entire solid or the entire crystal. While, and therefore there is a large scale picture to the metallic bond, and in covalent bonding and ionic bonding there is always a local picture which is predominantly important. Now, let us start with the topic of metallic crystals in a little more detail, and we will consider various aspects, especially of the common metallic crystals. We know that metallic crystals have positive ions placed at lattice points in a free electron cloud. So, the word free electron cloud here means a sea of electrons in which these ion cores reside. An important characteristic of metallic crystals is that the metallic bond are non-directional. This has important consequences when it comes to deformation behavior and all other properties of the metallic crystals. Since the bond is non-directional, typically there is a tendency of atoms to surround themselves with as many neighbors as possible. But we will see that this is not a perfect rule, but there is a tendency like that. And you will also find, again this is not a rule, this is a sort of a general observation which has quite a few exceptions, that the high temperature structure is typically open structure with respect to the lowest temperature structure, which is a more close packed structure. So, this is again a sort of a common observation in many metallic crystals. The partial covalent character of transition metals, which takes us back to this diagram, that actual bonding in many materials need not be purely metallic, ionic or covalent, and later on we will see examples of materials which have bonding characteristic between ionic and covalent, and in this case we are talking about bonding which is between metallic and covalent. We see that this partial covalent character or some covalent character in many transition metals for is a possible reason for many of them having a BCC structure, which is open structure at low temperatures. Typical metals you would notice are having one of these few structures. FCC is a close packed structure, and we will take up many examples later on. For instance, aluminium, iron under certain temperature regime and pressure regime, copper, silver, gold, nickel, palladium, platinum all have the FCC structure, and what I mean here is the cubic close packed structure. The BCC crystal common examples are lithium, sodium, potassium, titanium, zirconium, hafnium, niobium and many more. The other close packed structure which metals tend to form are the hexagonal close packed structure, which is beryllium, magnesium, titanium, zirconium, hafnium, zinc, etc. There are other lesser found crystals, like for instance we will take up a few of these examples later on in the chapter. Like for instance, polonium forms a simple cubic structure, which is a rare example because typically metals do not form simple cubic structure, they form more likely one of these structures, but polonium forms a simple cubic structure. Manganese can form more complex structures. For instance, the alpha manganese and beta manganese can have very complex structures, and we will consider some examples which have also these kind of complex structures. But the more important ones at our which will be the focus of our present study will the FCC, BCC and HCP crystals, and we will take up each one of these in lot of detail in this lecture.